Today in this class, we would like to discuss about the non-coherent FSK, non-coherent detection, and as well the non-coherent detection of FSK. So first of all, in non-coherent detection, what is the meaning of non-coherent detection? So in coherent detection, we are multiplying with the same orthogonal function phi1 of t or phi2 of t in the receiver. The same carrier signal, same orthogonal function. Like in non-coherent detection, so the phase is unknown because the detection we made with unknown phase. We don't know what is the phase at the receiver. For example, there is a phase variation, phase. So if that transmitted signal is root 2 e by t cos 2 pi f I t or something else, the transmitted signal, whereas the received signal with a delayed of phase something plus theta plus some white Gaussian noise is added. The receiver, if you design, either you acquire the carrier signal, that's different. If you detect the received signal with independent of phase, If you make detection with independent of phase, that is also non-coherent detection. Okay. Now, anyway, that white Gaussian is having some zero mean power spectral density and not by 2 and all. So I would like to find the detection process, the structure to make independent of phase. The output is independent of phase. For example, this is the signal either S of t and X of t. You can treat it as in general, S of t or X of t, whatever it is. With a delayed, what is that unknown phase? With unknown phase, this is unknown. Unknown phase. If you expand this cos A, cos B, cos A plus B, cos A, cos B plus sin A, sin B, anyway, this root 2e by t is the common factor. So cos 2 pi f I t cos theta plus sin 2 pi f I t sin theta. This is what the trigonometric property which you can find out, where you can treat it as root e cos theta 2 by t cos 2 pi f I t plus, okay, root sin theta multiplied with root 2 by t sin 2 pi f I t. This is the function. So anyway, this one is one factor and this is another factor. This is another factor. Root 2 by t cos 2 pi f I t, root 2 by t sin 2 pi f I t. These are both are orthogonal to each other. So this can be taken as pi 1 of t. This can be taken as pi 2 of t. Orthogonal to each other. So that this is where equal to root e cos theta pi 1 of t plus root e sin theta pi 2 of t. So that is what SI1 phi 1 of t plus SI2 phi 2 of t. So if you take squared sum of these squares and under roots. So this is what squaring e root e cos theta, squaring e cos square theta plus root e sin theta, squaring e sin square theta under root e into cos square theta plus sin square theta. It is 1. So under root, that is e Okay, so that is what root B. Okay, so this is what root of energy, either energy root EB or root E, whatever it is, that is the E, energy in this case where this root E. Okay, so this is independent of phase, independent of phase. And this is nothing but squared magnitude, this is an envelope, equivalent to envelope, equivalent to envelope, and this is independent of phase. So this non-coherent detection in orthogonal condition, phi 1 of t and phi 2 of t orthogonal to each other, while considering two orthonormal base functions in two different channels, multiplying in each channel this SI1 phi 1 of t plus SI2 phi 2 of t. Okay, where which is equivalent to squared magnitude of the squared values of these and under root. If you take that, so that is where the coefficient, if you find this is one of the correlator output of the coefficient, okay, and then take squares, sum, and again square root. So this is what we required in non-coherent detection. So this is what one correlator. This is one correlator. This is what SI1, and this is another correlator multiplying SI2. Okay, so this is where in phase channel of output of correlator YI SI1, quadrature phase channel, because these two cos and sine orthogonal to each other in the two different channels, upper and lower channels, we are getting in phase channel output, quadrature phase channel output YI and YQ as equivalent to SI1 and SI2. And squaring each, this is the squaring each SI1 square. Okay, this is SI2 square. And sum, you are getting sum and a square root. This is what square root of SI1 square plus SI2 square. Okay, SI2 square or YI square plus YQ square under root. So that is what output in the non-coherent detection, which is independent of phase. So as we know very well that each correlator, a correlator output is maximum, multiplier with an integrator, correlator output is maximum, is a matched filter, working as a matched filter, the output is maximum. Whichever is matched to this with this multiplier, phi 1 or phi 2, whichever is taken as output is maximized, so that input is matched to this phi I of t. Similarly here also, if this phi I of t cos 2 pi of I t match to cos 2 pi. If this output is matched to sin 2 pi of t phi 2, that is output, correlator output is matched to phi 2 or sin 2 pi of t. So either phi 1 or phi 2. So this is matched to phi 1 upper channel, matched to phi 2 the lower channel. That is why it is taken as a matched filter of cos 2 pi of t matched to phi 1 of t. This is matched to phi 2 of t. Okay, this is sin 2 pi of t. So this each correlator taken as a matched filter, and so that the remaining part of the squares and summation and the square root. This additional part is the envelope. This is what? Envelope. This is what? Envelope. And already this part correlators are matched filters and followed by envelope. So this is the matched filter followed by envelope. So this matched filter, whichever is matched to cos 2 pi ft. So then if it is matched to phi 1, it won't, the phi 2 output will be 0. If at all it is matched to phi 2, phi 1 output is 0. So considering these two are orthogonal to each other, okay, cos and sine, so phi I are related, having the relation orthogonal to each other, you can call it as cos and cos, cos 2 pi ft and cos 2 pi ft it, this phi I is having orthogonal relation, orthogonal condition, orthogonality each other. So this is how filter is matched to cos 2 pi ft followed by envelope detector. So output is taken and sampled at t equal to t maximum, the output will be taken as t. This is what non-coherent detection, which is equivalent to matched filter. So ultimately, in non-coherent detection, we take matched filter, match it to that corresponding orthogonal function phi I of t, and followed by envelope detector. This whole block diagram equals to this whole matched filter followed by envelope detector equals to two upper and lower channels matched filters and followed by squares summation square root of. This whole diagram is one matched filter and followed by envelope detector for every channel, So this is how then every channel having one matched filter followed by envelope detector. There are number of channels transmitting m number of signals S1 of t, S2 of t, etc. So this channel is matched to S1 of t followed by envelope detector taken as t, and similarly matched filter matched to S2 followed by envelope detector. So whenever we receive S1, upper channel output is maximum. Whenever S2 receive, lower channel output will be maximum. Accordingly, if you compare whichever channel output is maximum, for example, upper channel output L1, if it is maximum, L1 is greater than L2, then choose as S1. Choose as S1. Okay. L1 greater than L2, choose S1. If L2 is greater than L1, choose S2. That is how the non-coherent detection. Coming to, we discussed how the independent of phase in the non-coherent detection with unknown phase, the receiver system having a matched filter and as envelope detector, which gives the output independent of phase. We are applying in FSK system as we know the transmitting signal with F1 and F2 frequencies in FSK system for binary 1 and binary 0, and these two frequencies are orthogonal to each other. So the relation with 1 by TB separated with 1 by TB, and binary 1 F1 for binary 1 F1 frequency, binary 0 F2 frequency. So the transmitter and all same, but in the receiver system, we need to adopt the non-coherent detection where matched filter and envelope detector is followed. So which is independent of phase. So this is where the analogous to that non-coherent detection, matched filter envelope detector in the upper channel for binary 1, for S1 of T, matched filter and envelope detector for S2 at F2, S2 of T. So this is what for F1 frequency, and this is what for F2 frequency. So that is why this is matched to F1 cos 2 pi F1T, and this is matched to F2 cos 2 pi F2T, followed by envelope detector. So in the FSK system, if binary 1 is transmitted at frequency F1, upper channel output is maximum, L1 is greater than L2. If binary 1 is transmitted, that is S1. Then choose it as a binary 1 while comparing. If binary 0 is transmitted, that is S2, then L2 is greater than L1. So that is the lower channel output is maximum. So compare with the upper and lower, whichever output is maximum, that gives the output. So that is how the receiver, the coherent, non-coherent detection in case of FSK, frequency shift key. So in case of coherent detection, we just have a multiplier and integrator, that is a coherent correlator. Whereas in non-coherent detection, we have multiplier and integrator, the correlator as well, that is matched to that particular frequency, and followed by envelope detector, which gives the envelope of the that signal, which is the independent of phase, with the unknown phase having a non-coherent detection. So that's how the non-coherent detection of FSK we understand. So this is what we just taken. Okay. And whenever if both are equal, in case binary 1 or binary 0, you can guess either 0 or 1 if both the channels are output is 0. But as if that upper channel output is higher, corresponding to pi 1 F1 of T, F1 frequency, that is binary 1. If a lower channel output is 0, binary 0, that is what the decision making. So that is how the non-coherent detection in case of FSK system